All right, so today I'm going to be explaining this important paper from Max Welling in ICML 2022. Some papers only care about atom types and node types. They can be categorical distributions. So they only talk about 2D graph generation. Some people only consider the case of continuous 3D continuous, but without categorical features. They may use continuous features, but not categorical features. But some people, like this, the paper of this paper is combining categorical features with the continuous. And they also use equivariance to any group transformation, like rotation, any symmetric, like translation, rotation, any of these. And this is in 2022, so 3 years ago. This work introduces a diffusion model for equivariant to Euclidean transformation. So it is equivariant, the molecule generation, which is in 3D, is equivariant to Euclidean transformation. So this E3, this equivariant diffusion model, they call it EDM. This E3 learns to denoise the diffusion process with an equivariant network that jointly operates on both continuous and categorical features. Continuous, I mean XYZ coordinates because they are continuous. And if you have this molecule like this in 3D space, assume that this is molecule, and if you find the center of gravity, then everything is normalized. So every x, and because you need to have a good reference in order to make this work. And this is a good idea if you just take the central gravity. And in the appendix of this paper, they showed that about this center of gravity. So this is an overview of the EDM. To generate a molecule, a normal distributed set of points is denoised. These points, there is no just a set of points that have XYZ coordinates. And also we have H atom types. For example, this color is different from blue. Their atom types is different. So if, for example, carbon, oxygen, if you just rotate it 30 degree, it becomes this, carbon, oxygen. So it is rotating 30 degree. Still, the atom type is the same. Still, carbon, oxygen are the same. But so the probability of our X and X are equivalent. If you fix for a particular node type H, then P of X is equal to P of rotation matrix times X's coordinate. And so this is just the background that you are familiar with. And this is the loss that they have used, which is pretty standard. Everything is standard. So their main contribution is just this equivariance idea, that is orthogonal, this orthogonal R. For any orthogonal R, this relation holds. And they implemented using equivariant neural network that I've explained in the playlist for graph representation learning, several ideas to do that. So points and features, they consider point clouds with corresponding features. The features are invariant to group transformations, and the positions are affected by rotations, reflections, translations. So they use these equivariant graph neural network. They just use it. And here they say we first define an equivariant diffusion process for coordinates x sub I, and their atom features are h sub I. So they concatenate the atom features and the coordinates. So whenever they have this bracket, it means coordinate, they concatenate. And then here they do this generative denoising process. Again, everything is standard. Here they just use this. So they subtract. First of all, they subtract the center of gravity to make it normal. Otherwise, it's not generalizable because your reference could be anything. And then we sample the position and the atom coordinates, atom types from this distribution. So here they are training it. Here they are its inference. We are sampling. So we learned the equivariant dynamics function of the diffusion model using equivariant network, graph neural network. So their denoiser is equivariant graph neural network. In typical diffusion models, the data being modeled is ordinal, which marks, of course, in this paper, they didn't use any kind of ordering, and this is interesting, ordering on the nodes. Specifically, under very small noise perturbations of the original distributions, we have this. Because this Q is highly peak distribution, in practice it tends to 0 for all but one single discrete state of H. So this paragraph is interesting because the model, they just use this one hot encoder for the categorical, and then concatenate with the other features, so it becomes a longer vector. But the categorical is just the one hot encoder. For example, this one hot corresponds to carbon or anything else. And for continuous positions, defining L like that is a little more involved than for discrete features. A similar analysis, assuming P data, you can calculate this, which by completing the square, we find it equal to that distribution. When this parameterization is chosen, the log likelihood component can be written as the expectation of this. Now we are sampling x epsilon from this normal distribution that mean 0 and variance I. So since coordinate atom types and charges represent different physical quantities, we can define a relative scaling between them. While normalizing the features simply makes them easier to process for a neural network, the relative scaling has a deeper impact on the model. When the features are defined on a smaller scale than the coordinates, the denoising process tends to first determine rough positions and decide on the atom types only afterwards. Whereas scaling X requires a correction in the log likelihood since it is continuous. Scaling H does not require a correction and is not problematic as long as the difference in discrete values is large compared to sigma 0. So this is the negative log likelihood that you see in this table. Atom stability, for example, what is the percent, and molecular stability. So they have 10,000 samples, and they compare the metrics. So for the data, atom stability, of course, is 99. And for EDM, this is the atom stability. So they use these geom drugs datasets here. For QM9 samples is here. The first row is QM9. As you see, geom drugs are more complex molecules, like a real drug. And they say that QM9 only small molecules. Geom is a larger data set. It features 4,300,000 molecules up to, so it has 181 atoms and 44 atoms on average. So we present EDM and E3 equivariant diffusion model. While previous non-autoregressive models, autoregressive models are very slow in graph generation, one by one or a group by group. For example, in paired, you want to do it group by group. In Carnegie Mellon University, they developed this beautiful model for graph generation, but it is still slow because of that autoregressive property that at any time you add a couple of nodes, then another time you add another set of nodes. But because of the autoregressiveness of that, unlike mass diffusion, which is very parallel, paired is not. And in the Appendix 8, they talked about this zero center of gravity. Also, this basic thing from machine learning that it has explicit form. If you combine it with position and features, now it becomes like this. So the simplify objective is optimized during training. However, when evaluating the log likelihood of samples, the true weighting, 1 minus signal noise ratio of t minus 1 divided by signal noise ratio at time t, need to be used. So we follow the procedure described in algorithm 3. So they add this with the KL divergence. The base is the KL divergence, then we have L0 and LT.